In the previous video, we talked about searching for a particular value in our two linear abstract data types, array and list, and we observed that it can be done in theta n time. Okay? And we are wondering if it is possible to improve, upon this. But remember, if we have to read the whole data to solve any problem, in that case, the amount of efforts that are required to read the data of size n, they are theta n. Okay, so no matter what you do, the asymptotic time complexity of the resulting algorithm will be theta n or even worse than that. Okay, so here we already have an algorithm that takes theta n time. So when we say that we want to improve upon it, we want to have a faster algorithm, what it means? It means that we should not read the whole data, and that's the key. Okay, so when we are trying to design an algorithm for searching which is better than the linear time complexity, we should think about a way that will help us to search value, but still we will not read the whole data, and that seems counterintuitive. If I don't read the whole data, how can I declare the failure? Okay, so sometimes it can happen that I read only part of the data and I find the value that I am looking for. That's fine. Okay, but when we are going to declare failure, how can we do that without going through the whole data? Okay, we might be wrong. For example, if I am searching for value 38 in this particular array, okay, I cannot just read 0 and 1 and then say that, oh, value 38 is not present. Okay, because there are certain contents of this array which I have not read, which I have not checked, and without checking them, I am declaring the failure. Okay, so that is a problem if I don't read the whole data. So we have to balance this thing. Okay, we have to ensure that we do not read the whole data. Still, the answer that we give as the result of our search operation should be correct. Okay, so there should be no false positive, which means that if we say that the value is present, then it should be present. Okay, and there should be no false negative, which means that if we say that value is absent, then it must be absent in the data. So how can we achieve that? Okay, so that is possible if I read a particular value in my input, and I can declare that the certain part of my input is now irrelevant. So if I can eliminate a fraction of my input. Okay, so for example, I do one operation and my problem size changes from n to n by 2. Okay, and I do second operation and then my problem size changes from n by 2 to n by 4. Okay, and then I do a few operations, and what will happen? At some point of time, I would have made certain number of operations, and then finally my problem size will become 1. Okay, so if you notice, every time we are reducing the problem size by half, which means that this can go on of the order of log n steps, log n to the base 2 steps. So now here is a clue for designing our algorithm. We should design an algorithm that takes input of size n, and it is trying to solve the problem of searching a value v in this input of size n. It should perform only constant number of operations, and then it should either declare success, I found out the value that you are searching for, or it should reduce it to a problem where I am going to search for value v only in n by 2 problem size, and then we should continue in such a way. Okay, so how to achieve it? Okay, so this can be achieved if all my values in the array they're already in a particular order. Okay, so now let's take one quick example. Okay, so let's have an array with say 10 values. Okay, so I'm going to put in some random values, 5, 17, 21, 14, 8, 65, 1, 2, 3, 4, 5, 6, then let's have 80, then 9, 1, 2, 3, 4, 5, 6, 7, 8. Now we need two more numbers. Let's put 99 and 22. Okay, so let's say these are the 10 numbers given to me. So now if I try to search for any value, I have to go through all these values. However, if I arrange these numbers in say ascending order or descending order, it can help me to make my search more efficient. So let's arrange these numbers in the ascending order. So smallest of these numbers is 5. So I'm going to mark the numbers that I have already picked up. After 5, the next larger value is 8. So I'm going to pick up 8. After 8, I have 9. So 9 is the third element here. And after 9, what do I have? There is 14 here. So I'm going to pick up 14. After 14, I have 17. So next value is 17. Then we have 21. And then we have 22. Okay, and now out of the remaining numbers, I think 65 is the smallest one. And then comes 80. And in the end, 99. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All 10 numbers are here. And they are in the increasing order. 5, 8, 9, 14, 17, 21, 22, 65, 80, 99. Okay. How to transform this unordered input to the sorted one? That is about the sorting algorithms. And that will be covered in the second half of the semester by the second instructor. Okay. So for now, we will assume that there is a method that does the job. Okay. So let's not worry about how to do that. However, if I know that all my elements are in a particular order, and let's say they are stored in an array that is implemented as a set of contiguous memory locations, in that case, how I can do my array dot search operation given the value v. Okay. So what I can do is, I know this is the minimum value stored in the array. I know this is the maximum value stored in the array. And if I go to the middle, so I can go to 1, 2, 3, 4. So 0, 1, 2, 3, 4, 5. Okay, so I can go to this particular index, right? So what I will do is that I will take my array dot length and divide it by 2. So here array dot length is 10, right? And I divide it by 2. The answer is 5, which is actually the 6th element. Okay, index 5. So what I'll do is I'll take this as the index value and access this element and compare it against v. Okay, and there are 3 possibilities. What are those 3 possibilities? Well, either they are equal. In that case, I can declare success and I can return the value of this particular element. Okay. Otherwise, what should I do? I should consider the possibility that this value is less than v, and third possibility is greater than v. So in case the current value in array that I am looking at is less than v, so let's say I am searching for 65. In that case, there is no point in searching to the left of this side, right? Anything to the left of 21 is going to be less than 21, and then searching for v in this part is meaningless. So now I can focus only on the remaining part, the right hand part, the right hand half. So effectively what I have done is, now I have reduced my search problem from searching in an array of size 10 to searching in an array of size 4. And how many operations were required to do this? Well, I had to compute the middle element, that requires constant number of operations. I had to access that element, that again requires constant number of operations. And then I had to compare it with V, which also requires constant number of operations. So effectively with constant number of operations, I have reduced the problem size from n to n by 2 or even less than that. Okay. Consider the other possibility. If the middle value of the array, this 21, is greater than V. So let's say I am searching for 9. In that case, there is no point in searching to the right of 21. Searching in this part of 21 for 9 is going to be meaningless. So again, now my problem size is effectively reduced to 1, 2, 3, 4 and 5 elements. So from 10, my problem size is reduced to now 5. And number of operations performed are again constant number of operations. And then I can go and search there. Okay, so let's say the target value we are searching for is 65. Okay, so that would be this particular branch. So what I'll do is I will say that I'm going to search in array. Okay, but now I'll make it a bit more different. Okay, so I'll say that search for value V. Okay, and here is my left index and here is my right index. Okay, so my left index is 0 to begin with and my right index is going to be 9 to begin. So when I first call my array.search, I am going to search from 0 to 9, the whole array. And then instead of computing the middle element as length divided by 2, I will say that it is going to be right minus left divided by 2. Okay, so that's the change I will have. So I'll access the element A, right minus left divided by 2, and to that I have to add something. Okay, what is it? I have to add the value of left. Okay, because right minus left divided by 2 is going to give me the middle value, but sometimes I might start searching from 22. Okay, so in that case the index for 22 is 0, 1, 2, 3, 4, 5, 6, 9. Okay, so 9 minus 6 gives me 3 divided by 2 is 1, and to that I am going to add 6, so I'll have pointing to 7. So I'm going to divide this particular array into two parts, one to the left of this and one to the right of this. Okay, so that's the right way to partition my search space. Okay, so given the array and a value V to search, we are going to search from index left to index right, and when we begin, left is 0 and right is the largest index of my array. Okay, that's the way our search will start. We are going to point to this particular element. So when I begin, right is 9, left is 0, 9 minus 0 is 9 divided by 2 is 4, 4 plus 0 is 4. So I'm going to look at 0, 1, 2, 3, 4. So in this new logic, I'm going to divide my array into two parts, one to the left of 17, other to the right of 17. Okay, and first I'm going to compare it against 17. Okay, so let's write down what we are doing. So our first call is search for 9 starting from index 0 up to 9. Okay, and then what happens? We compare 9 against 17. So 9 is in the left of 17. Okay, so in that case, what is going to happen is, effectively we are going to search for value 9 starting from index 0 up to index 0, 1, 2, 3. Okay, because we have already compared against index 4. Okay, so now we are going to search for value 9 here, and again right is 3, left is 0. So 3 minus 0 is 3, 3 divided by 2 is 1, and 0 plus 1 is 1. So now 8 is going to be my partition element, index 1. Okay, so I am going to compare 9 with 8, and 9 if present it would be towards the right of 8. So what is going to happen is I am going to search for value 9 starting from index 2 going up to index 3. Okay, so now I'm going to again come back here and ask question. Right is 3, left is 2, 3 minus 2 is 1, 1 divided by 2 is 0, so left is 2, so 0, 1, 2, I'm going to compare against this element, and that's when I'm going to hit the success. Okay, so that's the way my binary search is going to work, and I required only 3 comparisons. Okay, so just think about the worst case scenario, what can happen. Okay, so out of 2 partitions that you create, you always pick up the larger partition as a result. Okay, so now we have 10 elements here, we pick up 1 element as the middle element, so surviving elements are 9. So we are going to create 2 sets. One is the set of 4 elements, other is going to be a set of 5 elements. And let's say we are going to search in a set of 5 elements. In that case, we are going to pick up 1 element again out of those 5 elements as the middle element, and then we might have to search in the left, which is 2 elements, and we might have to search on the right, which is again 2 elements. So in the worst case, we might have to search again in the set of 2 elements, and when you go and search in the set of 2 elements, what will happen is, depending on which element you pick up as the middle element, one partition is going to be empty and other partition is going to have 1 element. So in the worst case, we will again search in that single element. So in the worst case, you will still have 4 partitions, 4 search of comparisons. Okay, so that's how we are going to have only logarithmic time complexity for the search operation as compared to the linear search. Okay, so we'll say that when the elements in my array are ordered, I can do the binary search in theta log n time. Okay, so this log n, we are not specifying base, because any base it is going to be multiplied by constant. So we'll just say that it is log n. Okay, so let's write down this algorithm more clearly. Okay, so now I have the search operation, value v, left and right, and then we are going to compute the middle index. So we'll say that, oh, this middle index is equal to left plus right minus left divided by 2, and then we are going to do the comparison, right? So we'll ask question, if v is equal to a, or our more get element operation, right? That's the way we had written in our array at middle. Okay, so if we compare them and the result happens to be true, in that case we will return the middle. However, else, if, now we are going to give one more condition. What is that condition? The condition is that if v happens to be less than this get middle element, In that case, what should we do? Okay, so value that we are searching for is less than the middle element, then we should search in the left. So now I'm going to have a recursive call for my search operation. Okay, and then I'm going to search for value v. Yes, my left will still remain the same, it will not change. Okay, but what will happen is my right will become the middle value that I'm talking about, -1. Okay, because I have already compared against the middle value, so it will be middle -1. And whatever is the result of this, I'm going to simply return it. Return this particular result. Else, what should I do? I should search in the right partition. I would say that search for value v, going right up to the right one, but now search from middle +1. Okay, and whatever is the result of this, I'm going to return that result. Okay, but that's not all. Okay, so there are a few things that we need to tweak here, but this is the overall idea, and in the next video we'll see how to tweak this so that it becomes actually correct working pseudocode.